Okay, in the last video, we saw how to get the predicted value of y. We are going to compare the predicted value of y with the observed value of y, and we are going to look at how good is my model by looking at this comparison. If a lot of times my prediction has been right, then I would end up concluding that my model is good. On the other hand, if a lot of time my predictions are off, I have predicted that the student will not get job, student actually got the job, and the vice versa, then obviously my model is not good enough, right? So how do you evaluate a logistic regression model is the next obvious question to answer. Once again, recalling your memory. So what we are doing right now, we are essentially comparing the observed value of y with the predicted value of y. Okay, and we are asking ourselves, what is a good way to say that my logistic regression model is good? Okay, my logistic regression model is good. So there are very robust statistical methods that are used to calculate or evaluate the goodness of a model. Right? How do we say that the logistic regression model is quote unquote good? Right? So there are, as I said, there are statistical methods. Those are generally based on the log likelihood, the value of the log likelihood. You scan any statistics textbook and you will observe these statistical indicators. Deviance, which is I think -2 into LL. LL is log likelihood. -2 into LL. There are some R squared criteria. Even R squared is dependent on log likelihood. I think there is a square root formula which is again dependent on the value of the log likelihood. Again, -2 in the into log likelihood. There are some information criteria like Akai-Cape information criteria, Bayes information criteria, right? Now, these statistical indicators obviously cannot be taken in absolute sense. Whether the value of the statistical indicator is large value or small value may be again dependent on some statistical test. For example, some of these statistics have a chi-squared test statistic, the Akai-Cape information criteria, the Bayes information criteria, whether they are large or not significant are dependent on some chi-squared test, or the other indicators may be higher the better type. For example, R squared. R squared we never have any statistical test, right? R squared we say larger the better, right? That's what we saw in our MLR also. What was the criteria for R squared to be acceptable? We say as large as possible. So some of the statistical indicators may be of higher the better type also, and the example of higher the better type is R squared. The Akai-Cape information criteria, Bayes information criteria, they have a chi-squared test statistic. And once again, you know how to run those chi-squared test statistic. There is going to be a hypothesis that the logistic regression is significant or the logistic regression is not significant. You calculate the test statistic, which is a chi-squared test statistic. You compare that chi-squared test statistic with the tabular value of the chi-squared test statistic. And if the calculated value is more than the tabulated value, then you reject the null hypothesis and conclude that the logistic regression is significant, right? So that kind of thing. We are not going to go in that direction. We are not going to build a statistical test, chi-squared based test. Let us do that later when we see that in Python. For now, when we are evaluating everything in Excel, let us define some statistical indicators which are higher the better type, right? But we are not calculating R squared either. So what are we going to calculate? We are going to calculate three very commonly used statistical indicators. Those are called accuracy, precision, and recall. Obviously, this should tell us whether our logistic regression model is good or not, right? If my accuracy score is fairly large, I should be able to say, yeah, my logistic regression model is good. If my precision value calculated turns out to be fairly large, logistic regression is good. Same is true for recall. So we are going to actually calculate these three performance indicators for our example. Before we calculate these performance indicators, let us define these performance indicators. So let us define accuracy, precision and recall in the context of our logic regression model. Right, and as we can clearly see, they are larger the better type. What is the accuracy I want for my model? As large as possible. What is the recall I want for my model? Obviously larger the better. Right, higher the better, larger the better, whatever you call it. So let us define these accuracy, precision and recall. Okay, accuracy. How do we define accuracy? It is the measure of total predictions that a model got right. Okay, this includes both true positives and true negatives. So accuracy is just an overall measure. Tell me how many times you got it right. If you said y will be 1, was y actually 1? If you said y is equal to 0, was y actually 0? So obviously I am interested in the true positives as well as true negatives. Okay, I am interested in both y is equal to 1 matching in observation and in prediction, y is equal to 0 matching in observation and prediction. Okay, so tell me the total number of correct predictions for your model. How many times the model got it right? That's accuracy. Second evaluation criteria is recall. Okay, recall is the percentage of the response values that were actually captured by the model. Okay, what was the response value? Response value is y is equal to 1. Okay, the percentage of the response value that were captured. So there were certain number of y is equal to 1 in the observation. How many times did the model actually match with the observation when the observation was y is equal to 1? That is recall. And lastly, the precision. Precision is the measure of predicted value that were correct. When the model predicted y is equal to 1, was y actually 1? This is exactly opposite of what recall was. Okay, we'll discuss that in the next slide. We have that. So precision again is a measure of percentage of the predicted response values being correct. Okay, response values that we are interested in. So we will only take y is equal to 1, right? We will not take y is equal to 0. So for our student placement data, how do these evaluation criteria translate? Right. So for our response, for our student placement example, our response variable was binary and we were interested in one particular value, which is the student getting placed. Right. So we were interested in y is equal to 1. So how do we define accuracy? We define accuracy as the ratio of the total number of times the predicted and actual value matched, both for y is equal to 0 and y is equal to 1, to the total observations. What were the total observations in the sample? 27, because we had data for 27 students. Out of the 27 observations in the sample, how many times did the predicted and actual values matched, both for y is equal to 0 and y is equal to 1? That ratio is going to be defined as accuracy. Recall. Recall was how many times did the model correctly predict when the observation was y is equal to 1. Okay, so the total number of times that the prediction was y is equal to 1 to the total number of instances that the sample values were y is equal to 1. The observations were y is equal to 1. So here the total the total set is when the y was actually equal to 1 and how many times was my model able to capture that. Okay. Precision. If you want to take a minute to digest this, let us read it one more time. It is the ratio of number of times the prediction for y was 1 to the total number of instances where the y was actually 1. Okay. Precision on the other hand is exactly opposite. It is the ratio of number of times the y was actually 1 to the total number of instances where y was predicted to be 1. Right, exactly opposite. Exactly opposite. Okay, with these three definitions, let us evaluate our model. Okay, I hope you have understood these three evaluation criteria: accuracy, recall and precision. I actually want all these three to be as large as possible for me to conclude that my model is actually good. Makes sense, right? Accuracy, recall, and precision. Towards that, let us go back to Excel and calculate these performance indicator for our model. So once again, these are our observed value of y, and these are our predicted values of y. Okay, let us actually do this. So predicted values can be 0 or 1. Actual observed values can be 0 and 1. Okay, so from the data you can verify, it's only 27 values, you can verify that when y was actually 0, how many times did we actually predict that the y will be 0? 14 times. Okay, when y was actually 0, 3 times we ended up predicting that the y will be actually equal to 1. So this was wrong. This prediction was wrong. Similarly, this prediction was wrong. The actual value of y was 0. Our prediction turned out to be that y will be 0. Actual value of y was 1 and the predicted value of y was 0. We had 2 such instances. Okay. So this 3 and this 2 are incorrect predictions out of the 27 observations. So how do we calculate accuracy? What was our definition of accuracy? Our definition of accuracy was the total number of times our prediction was correct to the total number of observations. What is the total number of observations? Total number of observation is 27. How many times the prediction was right? 14. 14 times actual value of y was 0, predicted value of y was 0. Good. 8 times predicted value of y was 1, the actual value of y was 1. So 14 plus 8 matched, and therefore accuracy is calculated as 14 plus 8 divided by 27. What was precision? Oh, I calculated precision before recall. Here I have defined recall before precision. Doesn't matter. What was precision? Precision was the ratio of times the y was actually 1 to the total number of instances where the predicted value was 1. Where is the predicted value of y? Predicted value of y was 1 when it was actually 1 is 8, right? And what is the denominator? Denominator is the total number of instances where the prediction was 1. Total number of times the prediction was 1. What was the total number of times the prediction was 1? 11 times the prediction was 1. 11 times the prediction was 1. Out of these 11 times, 8 times the actual value of y was actually 1. So 8 divided by 11 is my precision of the model. 11 times totally my model predicted that y will be equal to 1. Out of those 11 times, 8 times y was actually 1. What was recall? Recall, first of all, let us get the denominator. It is the total number of instances where the sample value actually said y is observed to be 1. Y was actually 1. So where am I looking at? I am looking at this value. 10 times in the data, actually y was 1. 10 times in the data, y was actually 1. How many times was I able to recall that? 8 times my prediction was y will be equal to 1. Actually, 10 times y was equal to 1. Out of those 10, 8 times I correctly captured that. And therefore, my recall is 8 divided by 10. Once again, accuracy, recall, and precision. They are the performance indicators for my logistic regression model. I want them to be larger the better. I want them to be larger the better. Now let us go back and check how are these values influenced. These values are influenced by how many times did I get it right. How many times did I get it right and how many times did I miss it. So it depends on my predicted value of y. Now where are these predicted values of y coming from? My predicted values of y are coming from the probability of day 0, which is predicted by the model, which is calculated by the model, and more importantly by the cutoff. Right? Remember earlier we said this cutoff seems to be arbitrary. This cutoff seems to be arbitrary. Now if I change the cutoff from 0.5 to let us say 0.6, any probability which is lesser than 0.6 will be classified as y is equal to 0. any probability which is more than 0.6 will be classified as y is equal to 1, right? So the predicted value of y's depends on this cutoff, and therefore the accuracy, precision and recall should also depend on this definition of my threshold. This definition of my threshold, whether you call it cutoff, you call it threshold, it's the same thing. It's the same thing. Okay, so if I change the cutoff from 0.4 to let us say from 0.5 to let us say 0.4, the accuracy values should change, right? Accuracy values should change. Can I see that? Can I see how does the accuracy, precision and recall change if I change this cutoff? And then I should be able to correctly set the value of the threshold, which gives me the maximum possible value of accuracy, precision and recall, right? That should be the correct approach. Well, that's what we have done. So these are the various values of cutoff. Cutoff could be 0, 0.1, 0.2, 0.3, 0.4, 0.5 all the way to 0.9. And these are the various values of accuracy, precision and recall. Notice that precision and recall, they were exactly opposite of each other, and therefore they are moving in the opposite direction. They are moving in the opposite direction. When precision is quite large, the recall is quite low. When the recall is quite large, precision seems to be quite low, right? Expected, because that's how we defined them. All right. What do we need to do? What do we need to do? We need to change the cutoff to, let us say 0.1, 0.1. Calculate all these values. Calculate all these values. Oops. Okay, I have not set up the. Yeah, it is set up correctly. It is set up correctly. So when the cutoff is 0.1, the accuracy is 0.7778, precision is 1, and recall is 0.647. Right? When the cutoff is 0.2, okay, when the cutoff is 0.2, my accuracy goes up. Earlier it was 0.77, now my accuracy is 0.81. My precision remains 1, but my recall goes up. My recall goes up. So 0.1 seems to be inferior, and 0.2 seems to be a better value. I'll keep doing this. Keep going all the way to 0.9. Before I do that, let me set that to 0.5 as my default threshold. Okay, that's how we saw the calculations. And let us look at the plot of this. Let us reduce the zoom a little bit so that I can fit that into the screen. Okay, so as the cutoffs, I need to show the plots also. Okay. So as the cutoff increases, as the threshold probability increases, the blue curve is the accuracy curve, the orange curve is the precision curve, and the gray curve is the recall curve, right? So looks to me, right, if I set the threshold to be too low, my precision will be quite large, but I will take a hit in recall. Whereas if I set the threshold to be too large, my precision will take a hit, but I will perform very well on recall. So somewhere in this region is where I seem to be doing well. Somewhere in this region is where I seem to be doing all right. So somewhere in this region, probably 0.4, from there looks like 0.4. 0.4 seems to be a good threshold to be set. Okay, but that's the conclusion. Let us go back to evaluation. How did we evaluate our logistic regression model? We evaluated our logistic regression model on 3 parameters: accuracy, recall and precision. All 3 of them are higher the better kind of criteria. I want all 3 values to be large, and therefore I said that the threshold probability to classify y is equal to 0 or y is equal to 1 will be set based on getting the maximum possible value of accuracy, precision, and recall. And there is a trade-off. What is the trade-off? We saw that precision and recall seems to be moving in the opposite direction. Right? What is another quick way of checking whether my model is correct or not? This is a very analytical way of looking at whether my model is correct or not. Right? This should take precedence. The other way to look at whether my model is right or wrong is to quickly look at the plots. Right? So I have not done anything different. All the data is exactly the same. Now I have plotted, right, probability of y is equal to 1, predicted value of probability of y is equal to 1 against the MBA CGPA during the MBA program. Let us zoom it in a little bit. Take a closer look at this. Okay, take a closer look at this, and clearly we seem to be able to see that when the CGPA is low, when the MBA CGPA is low, the probability that the student will get placed is low. As the CGPA increases, there seems to be a sudden spike, right? Sudden spike, and obviously it is a probability, so it has to taper off at 1. Right, so this is that famous S curve, right? Obviously our S curve is not very precise, but this is what I would have expected my response variable to behave, right? Now go back. For MBA CGPA, my beta was positive, my beta was 3.27, and therefore it resulted in this kind of a response behavior when we looked at one of the explanatory variables, right? So we can look at this and we'll say that, well, yeah, the model seems to be behaving the way I expected the model to behave. But this is a more precise way. This is a more analytically correct method of deciding whether my model is good. So looking at these numbers, right, even if I look at 0.4, I get the maximum accuracy of 0.85, and my precision and recall are 0.81 and 81 respectively, same values. This seems to be the best combination. And looking at these values, 85% accuracy, 81% precision, 81% recall, I would say, yeah, good, my model is not doing bad. And therefore, that's one way of concluding that what we have done in this Excel is not such a bad thing to do. Once again, we are going to end the session here, and the last thing to be done is estimate or understanding what these betas mean. Let us pause here for a moment and continue in a moment.